4, 6. There's a set with only 3 elements in it. This is what's called a subset of that larger set we saw on the other page. 2, 4, 6, 8, 10, etc. The other set of real even numbers. You see that these 3 elements are contained in this set. This is a smaller set. This is a subset of the larger set. So if you were to look at this in a picture, say, if this shape describes the set, then what we have here is a small part of that set called a subset. Now, I will use that terminology throughout the course, and if we need to say anything more about sets about this, we'll introduce that terminology as we go. But now let's go back to the list and see what kind of numbers we'll first look at. We'll first look at natural numbers. These are sometimes called the counting numbers. What are they? Natural numbers. These are numbers that we really take for granted. These are numbers that we didn't have to invent, as we have to invent other numbers. These numbers can be thought of as just existing. They are often denoted, the set is often denoted by a bold-faced M, and that's the way I'll write that. And what is this set? Well, it consists of these numbers, 1, 2, 3, 4, etc. And then sometimes we do this also. We put an N here to indicate the variable that I will use, or that I will use to stand for such numbers, and then a comma and continue on out to infinity. So this is a commonly used variable for natural numbers, and I'll use it from time to time. These will be taken as given. These are not invented. There's nothing to describe. These are simply the starting place for the number systems we'll look at. But you know, there are lots of numbers within this set of numbers that are quite interesting. So let's go ahead and talk about a few of them, because they will have bearing later. There's a set of numbers that are called prime numbers. Why would I want to talk about those? Well, as in chemistry, it is helpful to look at what you might consider the atoms of the material that you are discussing. Prime numbers can be considered the atoms of the natural numbers. For example, let's go ahead and define what a prime number is. P is prime. Called a prime number if, well, first of all, P is greater than 1. 1 is not considered a prime number. And what makes a prime number an atom? P is divisible only by 2 things. Only by 1, which divides it to every number, and itself, P. What do these numbers look like? Well, I'm sure you've seen these in your life. The set of prime numbers looks like this. The first one is 2, which happens to be the only even prime number. Then 3, 5, 7, not 9, because remember 9 would be 3 times 3. 11, 13, 17, etc. There are infinite number of primes, and this is what they look like. Numbers like this. They're only divisible, they can only be factored, words that I will be describing soon, into themselves times 1. So those are prime numbers. Now with prime numbers, since we can think of them as the atoms of the natural numbers, you might expect that we ought to be able to write all natural numbers in terms of prime numbers, and so we can. So this is such a famous result, I just want to go ahead and introduce it to you. It's called the fundamental theorem. Fundamental theorem of arithmetic. Arithmetic, you may ask. Why are we studying arithmetic in the algebra course? Well, as you see, it really is going to be the basis for much of what we do. And it's not really a theorem you haven't seen in this form, but I think you know what it's going to say. Any natural number, that is to say, any of those counting numbers we saw before, any natural number can be factored. Now, I haven't officially defined the word factor, but a factor is simply a thing that is multiplied. So to factor a number like 12 would be to write it as a product of 2 other numbers. It can be factored uniquely. There's only one way you can factor it, and that one way is except for the order of the factors. Except for the order of the factors. Because as you may remember from your knowledge of the numbers, that numbers like 2 times 3 are the same thing as numbers 3 times 2 into a product of prime powers. Prime numbers, prime powers. So, here we say this one more time. Any natural number can be factored uniquely, except for the order of the factors, into a product of prime powers. Now, let me give you some examples, so you'll know what it is I'm saying here. And once I do, I think you'll see that this is familiar. Let me take the number I mentioned a moment ago, 12. 12, as you know, can be written as 3 times 4. That may be the first thing that comes to mind. But 4 can be written as 2 squared. So this can be written as 2 squared times 3. Now, 2 is a prime number, 2 a power. This is 2 times 2. That's what the 2 up there means. And 3 is another prime number. Let me do a few more examples. 70 can be written as 2 times 5 times 7, for example. 111 can be written as 3 times 37, etc. All the natural numbers can be written as products of prime numbers, or possibly powers of prime numbers. And as I said before, we'll define it again in a little bit. Factors are things that are multiplied. Now, before I leave this topic, I want to mislead you. Generally, factoring numbers is hard. If you start with a very large number and you try to factor it, it is very hard to do. In fact, that's being used in security systems these days for that very reason. But the kind of factoring we will do is fairly simple. And so I'll pause now and give you a chance to remind yourself of a few things. Now we'll continue our development of the numbers by looking at integers. So what are the integers? The integers are the larger set of the natural numbers. The integers are often denoted by a capital Z. You may say, what does that have to do with integers? There's no Z in the word integer. Well, just for the historically minded among you, this comes from the German word Zahlen, which stands for numbers. So that's what the symbolism comes from. And what are the integers? How are they different from the natural numbers? Well, so the way I'm going to define the integers is to give you a sense of why one would need the numbers. So let's imagine that we're moving ahead in the course here. We want to solve a certain very simple equation. Suppose we want to solve the equation x plus 1 equals 1. We want to find a number x that will make this equation true. Well, you know from your own experience that there is only one number that will make this true. We need what? We need the number 0. Like in the natural numbers, there is no 0. So 0 has to be added to that, and that will become one of the integers. Let me show you one other small equation to suggest why we need another set of numbers. Suppose we want to solve x plus 1 equals 0 using that number 0. Now, from what you know, what would you have to add to 1 to get 0? Well, you have to add, we need a number like minus 1. Again, the natural numbers don't have any negative numbers in them, so we have to add these numbers in. So when we add them all in, we're going to get a set that is the integers. Here is that set. The set C, and it will be infinite in both directions, so we'll have to start off with dots. And then I'll give you a few of the numbers, minus 4, minus 3, minus 2, minus 1. Then there's a special number 0, so I'll put it on its own line alone. And then we'll continue 1, 2, 3, 4, etc. out to infinity. Now, there's a more compact way to write this, so I'll show you that. If we put 0 at the front, and then we put a plus and a minus sign here for 1, So we can imagine plus 1 and minus 1 being next to each other. And then plus or minus 2, plus or minus 3, plus or minus 4, etc. out to infinity. Now this is just more compact. So this is a more compact way of writing this set. We've now expanded our set of numbers. We no longer have simply the natural numbers. Notice that the natural numbers are right here. They're included in the integers. We have added 0 and we've added all these negative numbers. And a reasonable way of describing the reason for that is to say that we needed to solve certain kinds of equations. So let me show you a couple of things in an example about these numbers. These are things you probably have seen much of your life. I'll just remind you of a couple of things. For example, if I take 0 times 5, now notice I've already started introducing a notation that you may not be familiar with. I'm using a dot for multiplication. Again, I will talk about that a little bit later on. But you can see that I'm multiplying 0 times 5. Well, you know what happens when you multiply a number times 0. You get 0. So there's a fact from your past, I hope. Now we take 0 times 82, we're going to get 0. It doesn't matter what number you choose. 0 times that number is 0. What else can we say? How about 0 plus a number, like 0 plus 7? Well, that is 7. The 0 contributes nothing. So you know that adding 0 to any number will result in the original number coming back. How about negative numbers? What are some of the properties you probably have seen before? Well, suppose we take two numbers like minus 5 and minus 2 and multiply them together. Well, you'll get 10. In fact, you get plus 10 because a negative times a negative is a positive. What about an addition problem? Take minus 5 plus 2. Well, as you know, 2 minus 5 will give me a minus 3, etc. So the kinds of facts that you should be familiar with are the facts about the elementary integers and the properties they have. So let's go ahead and look at another set of numbers that is built from integers. So we'll go back to my list. And after integers, we will look at rational numbers. This is where we take integers and we create a new set of numbers. And I'll show you exactly how that's done. Rational numbers. Now, rational numbers have their own bold-faced letter symbol, Q. And this time the Q stands for quotient, so that seems to make good sense. What does a rational number look like? Well, they're what you previously called in grammar school fractions. P over Q. That is a rational number. What are the P and Q? The P and the Q are integers. So they come from that set C that we saw a moment ago. And we also say that Q is not 0. Now we're forbidding the bottom to be 0. The bottom of the fraction is not 0, and I'll explain why in a little bit, but we're going to say that division by 0 is not allowed. It is undefined. There's a good reason for that. But this, of course, is what you called before as I said a fraction. You might also have used the word ratio, which is where rational comes from in the description of these. And now let's look at a few examples. Just to remind you what we're talking about here. Examples, you know what we saw. 1/2, 2/3, 11/13, 574 over 201, etc. Those are all examples of rational numbers. They're fractions. Some of them, as is the case of the last one, are being proper fractions. The top is bigger than the bottom, but they're still rational numbers. Now, let me note that once again we have increased our number system without losing anything. All n is in Q. In fact, all z, the integers, all of that set is in Q. How do I know that? Well, since if you take a number n from either z or the natural numbers and you put it over 1, lo and behold, you have a rational number. But of course, n over 1 is still n. And so these numbers from here can be rewritten as n over 1, and they appear as rational numbers. And, for example, 8 over 1, of course, is 8 and so on. So that's what rational numbers look like. Now, I said a moment ago that division by 0 is not allowed in the rational numbers. So let me go ahead and give you that warning and give you a reason why that is true. So we don't have any mysteries here. Warning. Division by 0 is what's called undefined. Now you might say, well, it's undefined. Why does somebody define it? Well, there's a reason it's undefined. Because you cannot define it as a number and end up without a contradiction. So the answer is why. The question rather is why. Why is it undefined? Here's why. Let us suppose. Let's take a simple case. Because if it fails here, it's probably going to fail for the rest. Here, all the properties of the other numbers we've seen satisfy. So that is going to lead us to a problem. Watch. Again, consider the following situation. And this is just one of many possible situations I can describe. Consider the following. 0 times this new purported number 1 over 0. Now, I can make two different arguments. On the one hand, I can say this must be 0. Why? Here's my reason. Since, as we saw a moment ago, 0 times x equals 0 for any number that we've seen x. You multiply number by 0, give it 0. That's what I've done here. Multiply this purported number by 0. So I claim it's 0. Fine. On the other hand, I can also make the following argument. That this is equal to 1. And what's my reason there? Since, copying what I have here, if you have x times 1 over x, that's the same as x over x, and of course